Nice to hear you. All right. Sorry for my delay, but I've got some phone from my boss, from professor. So that's the reason why we're starting 5 minutes after the time. All right. Okay, so today I'm going to show you how solve some electronic circuits which contains, for example, the transistor. Because to this moment, in fact, we are operating with the typical components, fundamental components in electronics, like the resistances, the capacitors, or the coils. So I think it's time to show you some real electronic circuits with resistors, with transistors, and how we can calculating this circuits. All right. First of all, please tell me, do you hear something about the transistors? Means, for example, bipolar transistor or a JFET transistor. Do you hear something about it? Hello? Guys, do you hear something about the transistors?
No.
Okay. All right. So, first of all, we have to know what is it, the transistor. Of course, in the next semester, I think you will have some electronic circuit classes also, or some lecture about it. However, you have to know the basic information about it. Okay, we've got a lot of type of transistors. However, at this moment, I want to focus on the one of them. It is the bipolar transistor. What is the transistor? This is the element with 3 terminals. For the bipolar one, it is the terminals named like the collector, emitter, and the base. What is something special with transistor? What the properties we used using such component in electronic circuits? In fact, this is the amplification of the current. That's why the transistors are used in the amplifier circuits. For example, let's say we want to build some, for example, the headphone amplifier, let's say. So we can use the transistor, bipolar transistor in amplifier configuration. But basically, what is the symbol of the bipolar transistor? It is like that. This is the arrow, and this is the collector. This is the emitter. Emitter, it is the terminal which is connected with this arrow. We've got 2 types of such transistor, NPN and PNP. Why? Because if you take the part of the piece of the material, the semiconductor material, or the structure of this transistor, we'll see that it can be built in different way. We can doping the semiconductor materials to get the P material, N and P material again, or N, P. And what does it mean? The P means that we have much more whole places where there previously was some electronics. It means we've got the much more positive charges. The N, it is the material which is doped by the other one, and in consequence we'll have much more electrons there. And the P is also the material where we have a lot of holes, which means it is the same, like we will have the positive charges. And in the place between the N and P materials, we've got the junction, the NP junction. This junction can be polarized in conductive way or in the opposite way. At this moment, it doesn't matter what happened, especially here. However, you have to know that this is the structure of the bipolar transistor, two types of them. That's why you can see that we've got the PNP or NPN structure. Okay, how we can show it using the symbol of transistor, which one it is PNP and which one it is NPN. If the arrow is outgoing, it means this is the NPN transistor. If we'll have the PNP one, the symbol of it is like that. All right. Great. So here we've got the connection of the collector. Here we've got the connection of the emitter, and here only to the P structure we've got the base. Something was happened with my okay, maybe I use it. All right. We need much more light. Okay. So, so as you see, it depends which type of transistor we've got. We have to connect this transistor to our electronic circuits in a correct way. How? If we have the NPN transistor, it means that the current of the collector should entering here. The base current should entering to it also, and this current from the emitter should leaving the transistor. Okay, that's the polarity of the NPN transistor. If we have the PNP transistor, it is everything is opposite, which means that the current should entering to the emitter, and from the base and from the collector, the current should leaving. All right. So how works the transistor? You can say, look, this is like the water valve. Yeah. Please imagine that we've got some pipe, This is the pipe. Here we've got the valve. Yeah. And here we'll have some water inside the pipe. However, if we know, if we use this screw and we turn off the valve, we stop the water flow through the pipe. Yeah. And now, if you try to imagine that this water flow, in fact, this is the current. So you can see that using the valve, we can controlling the current which is passing through from the top to bottom part of the pipe. So, okay, so let's name this top part of the pipe like the collector, and this is the emitter. Okay, so as you see, how we can controlling the current between the collector and the emitter, we can control it by the valve. However, in the transistor, our valve, in fact, this is the base current. You have to know that if we have the bipolar transistor, we can controlling the current between collector and emitter by the current on the base. If you take the, for example, CMOS transistor or JFET transistor, then we can controlling the current between the drain and source by voltage drop on gate. So as you see, we've got, it depends what type of transistor we've got. We've got a different type of controlling of the current. Using it, we can control the current by base current or voltage drop on the base. In fact, in such transistor, this base is named like the gate. So the more important is the current here, the base current. And if the base current increasing, then the higher current between the collector and emitter can passing through the transistor. If the current is decreasing, the collector current is decreasing too. And for example, if the base current is equal 0, it means that the transistor is turned off. What does it mean is turned off? The current, the collector current is stopped flowing. It is the situation when we turn on the turn off the valve. Yeah, everything is blocked. The water is blocked. There's no passing through. What does it mean due to electronic point of view? It means that the resistance in the material between the collector and emitter here, the resistance is so huge. It's very, very big. Yeah, that's why the current can passing through by this component due to huge resistance. Okay, and the opposite situation when the base current is so, maybe not so big, but have some, for example, the thousands of microamperes only. However, it is so huge for the base current. It means that the transistor is open. It means that we've got the IC current, which is passing through by our transistor, and the resistance between the collector and emitter is very low. For ideal situation, when the transistor is open, it means that the voltage drop between the collector emitter should be how many for ideal situation? What do you think? When the transistor is open?
0.7 volt.
No. I see that you, Jakub, I think you heard something about the transistors, yeah?
Just a little bit.
Okay. No. Look, I'm asking you what will be the voltage drop between the emitter and the collector when the transistor is open. So I tell
for a perfect transistor.
Yeah, for the perfect transistor.
When it's open.
Yeah, when it is open. So
it should be the maximum voltage?
No.
I mean the collector voltage?
Right. So look, you have to be very, very careful what I said. If the transistor is open, maximum open, it means that its resistances is
the lowest.
The lowest one. Okay, for ideal situation, the resistances is equal
Zero.
Yeah, that's right. Then the ideal transistor is fully open. The resistance is equal 0. It means that the voltage drop between emitter and the collector should be how many? When the resistance is 0? Of course, yes, Igor. So it should be the 0 volts. It means that the resistance is 0. However, in a real transistor, even it is fully open, we have to remember that we've got some structure inside of the materials. As you know, here we've got the materials where we've got a lot of electrons. However, any materials, even they are conductors, they have some resistances. Yeah, very low, however, they have. That means even the transistor is open for the real one, we have some resistances. This resistance is very low. However, it produced the saturation voltage between the collector emitter. It is called like UCS SAT, and this is for the silicon transistor, bipolar transistor. It is 0.2 volts around. So sometimes we have to take it into account in calculations. Okay, so what else? So I think at the beginning it's enough. Oh, maybe not. Please try to remember that bipolar transistor is controlled by the base current. And when the base current is going up, then the resistance of our transistor between collector emitter decreasing, so we can observe some current flow through the collector emitter here, like in the water pipeline. What else? When the base current reach some point limit, for example, thousands of microamperes, then we'll see saturation between the current and emitter, which means that the resistance between these two terminals is the lowest one that can be. And this resistance is equal 0.2 volts. right? Great. So what else? In such transistor, the bipolar transistor, you have to know that we've got some relationship between the base current and the collector current. The one of them, it is like that. IC current, the collector current, is equal beta times IB. What is the beta? Beta, this is the parameter of the transistor. And this is named like the current amplification of the transistor. Current amplification of the transistor. So according to this formula, we can very briefly find the beta. The beta, it is IC over IB. Okay. So if you're going to the shop and you want to buy some transistor, you can find the transistor which has the beta. The beta can be equal 18 times, or for some transistor, it can reach, for example, 800 also. Yeah. So it depends on what type of transistor you will buy. Okay. However, the beta is very important parameter because it tells you what will be the IC current when the current beta is equal, for example, 1 microamperes. Then you will very briefly calculating what will be the IC current, which is passing through by the collector emitter. One thing, if you take a look at this transistor scheme or the symbol, it is very simple to understand or remember the current flow in such transistor. Anytime in the NPN transistor, the collector current is entering here, the base is entering here, and these two currents is adding here, and they passing through together and leaving the emitter. Okay. So as you see, as I said at the beginning, in fact, the current, the collector current, it is in fact not the same current like the emitter current. Why? Because the emitter current, it is equal, how many? IC plus IB. Okay, anytime. Okay, so these two expressions you have to know definitely if you are try to solve some circuit using this type of transistor. Okay, so please tell me. At this moment, I give you the fundamental knowledge about, very quickly, I told you about it, about the transistors. Do you understand it? Please tell me. Hello, are you there? Do you understand it? Maybe yes. Okay. And some people write on the chat. Okay. All right. Great. So, and again, please tell me, the question is about the polarity of the transistor. So, to force such current flow direction through our transistor, what should be the polarity of the collector, base, and emitter? It means where we have to plug in the positive, the plus potential, and where we have to put the minus one.
If I remember correctly, simple switch would be emitter to ground, collector to voltage, and base. I think around 0.7 volts to turn on transistor.
Okay, but Jakub, you are just trying to reproducing something from your mind about the transistor. That's right?
Yeah.
Okay, but I wanted to force you to start thinking. I told you the current directions on the base, collector, and emitter. So you don't have to remember this information, and you don't have to search it in your mind. However, just know that the current is passing from the positive to negative, plus to minus potential. So it is very simple. Look, the current IC should passing through in that direction and is entering to the transistor and leaving it like the emitter current in that direction. It means that here we'll have to have the positive potential, then here, that's right. Only in that polarity we can get such a way of the current flow. And also, as you see, the base current should enter into it, and we know that this base current is adding with the collector current, giving the emitter current. So as you see, also according to this point, the base should has also the positive potential than this. Yeah, I think it is simple. So that's why if we've got the bipolar transistor in the NPN form, the polarity should be like that. Great. So I think it is enough the introduction with the transistor, and now we can start to find the current in very, very simple amplifier built on or based on the transistor, bipolar transistor. All right. Please imagine that we've got okay, please note it, of course. Okay. Please give me some few seconds to find something better to some pen, or I don't know, to
need to
All right. So sorry, I'm back. All right. So this is the transistor here. And the question is, okay, how we can build the simple the amplifier here. Okay, here we have to add the capacitor. This is our, oh, sorry. This is our input. Here we have to adding some capacitor again, and this is our output. And we have to, okay, this is the junctions. At this moment, we have to supply our amplifier. So it means we have to put some potentials to the collector, emitter, and the base properly, yeah, or according to the type of it. We know that this is the NPN transistor. So the collector should has the higher potential than emitter, and the base should has the higher potential than emitter too. So as you see here, we can plug in the ground. So this is our 0 volts, and this is our plus VC. Yeah, this is our our power supply is plugged in here. Okay, for example, 12 volts. For example. All right. So in this example, we've got that values. RB, the base resistor, it is 220 kilos. The collector resistor, it is 1 kilo ohms. The emitter resistor, it is the 50 ohms, for example. Or maybe not. 510 ohms. Sorry. Okay, VC, it is, let's say, 10 volts. Okay. Okay. The beta of the transistor, it is 100. And what you have to know about the bipolar transistor, if you plug in the transistor to the electronic circuit and we turn on the power, the voltage drop between polarized junction between the emitter and the base, giving you some voltage drop here, which is named the UBE, voltage drop. And for the silicon bipolar transistor, it is equal around 0.7 volts. Much more precisely, it is around 0.65, something like that. Yeah. We can at this moment we can write that it's 0.6 volts. Okay. All right. So what we have to do, we have to find the base current. We have to know, we have to find the collector current, and what is the UCE voltage drop between the collector and the emitter. Okay, so how we can find this currents here, currents and voltage. First of all, please take a look at our electronic circuits at this moment, and what we have to do, we have to just find the currents or indicates the current in this case. So as you see, if we plug in the VC voltage, we'll see that here we've got the junction. So the current should flowing from the positive to negative potential. It means from the UCC to the ground. All right. So this current is going to the junction, and it is divided by two currents. This current, it is passing through, as you see, through the RB resistor, and here in this point, because this is the DC voltage, so also this is the DC current. So in this point, this current cannot going to the input junction because we've got the capacitor. So this is between these two places, we've got the electric materials. So this current can passing through here and entering to the base of transistor. So as you see, this current and this one are the same, and this current is entering to the base. So we can name it like the IB current. All right. What is it? This current is passing through by RC resistor, and it is also in this point cannot passing through to the output because we've got the capacitor. So the DC current can only going to the collector terminal. So as you see, this current and this one, it is the same current, and this current is entering to the collector. So we can name it like the IC current. And also the current here, which is entering the emitter, which is leaving the emitter, is passing through by the RE resistor and is going to the 0. So in fact, we've got the IE current. Okay, so let's mark the voltage drops on this resistances. So here, so it is the voltage drop on the RB resistor will be URB. Yeah. Voltage drop on the collector will be here, URC. Voltage drop on the emitter will be here, and this is the URE. All right, great. What else? We know the Kirchhoff's law, and if we've got the power supply here, the VC, and the 0 is here, so any voltage drop in this in this branch should give us the VCC value. Yeah? So what we have in here, we forget about the voltage drop between emitter and the collector. Yeah. All right. So at this moment, let's find the formula for this circuit. Okay, let's take it into account this branch. So for this branch, using the Kirchhoff voltage law, we know that VCC, yeah, this is the voltage drop between ground and this point, should be equal, yeah, should be equal the sum of the voltage drop on this resistor between the collector emitter plus the URE, voltage drop on the emitter. Yeah? This 3 voltage drops should give us the total VC voltage. So we can draw it in that form, that VC minus voltage drop on the RC minus UCE minus URE should be equal 0. Yeah. Okay. This is the first branch, first equation. All right. The next step. Look, because we have to find the currents also. We've got the voltage drop, URC, URE. So using the Ohm law, we can express this voltage drop by the current and by the resistances. So let's do it. So VCC minus URC, it is the voltage drop on the RC resistances. So what will be the voltage drop according to the Ohm law? What will be the equal the URC? It is the IC current times RC. Yeah. Minus UCE, it is voltage drop between emitter and the collector, and we have to find them, yeah, because it is our case in this example, and minus URE. So this is the current IE times RE, IE times RE, and everything is equal to 0. Great. Okay. So in the next step, we have to connect. First of all, let's take a look what we have to find. We have to find UCE. We have to find the IC current and IB current. Okay, so as you see, we've got the first equation where we have unknown value IC, UC, and IE. Okay, however, I told you that the IE current, it is equal, what? This is the sum of the IC plus IB. Okay. However, maybe you remember what is the beta. Do you remember the beta value? How we can find the beta? It is the current amplification of the current.
IC over IB.
Yeah, IC over IB. So from this formula, IC, it is equal beta IB. Yeah. So we can substitute by IC the beta times IB. So that's why IE can be expressed like that formula. Yeah. So if you extract the IB, we've got the beta plus 1 here times IB. Okay, so our first equation at this moment looks like that. VCC minus ICRC minus UCE minus IB times beta plus 1 times RE. Great. So as you see, we've got the first equation with 3 unknowns value, IC, UC, IB. So we need the extra formulas. Okay, So let's consider the next branch, which is going from the VC here, 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 and here. Okay, so as you see also the voltage drop on the components here should give us the VC voltage too. Yeah, so, oh sorry. So the second formula for the second branch, it will be the VCC minus URB minus UBE minus URE. Okay. This voltage drop plus this one should give us the VCC value. Okay, so we have to do the same like here. Let's substitute by the voltages using the Ohm law, of course, the relationship with the with current and the resistances. Okay, so this is the VCC minus URB. It is the IB times RB minus UBE. Okay, minus IE RE. Okay. Okay, so we've got it. But we can change the current IE by this formula. Yeah. So we've got the VCC minus IB, RB minus UBE minus IB beta plus 1 times RE. It is equal 0. Right. So as you see, we've got the second formula. Right. But please take a look what happened here. We've got the VC. See, UBE is known. Everything is known without the IB. So in this formula, because in fact, this is our next expressions. Yeah, using it, we reduce in fact numbers of the equations here, and we make it the substitute in this moment. That's why we can directly calculating the current IB from this second formula. What will be the IB here? Look, okay, first of all, everything with the minus values, let's move it to the right side of the equation and change the sign to the opposite. So we'll have the IBRB plus IB beta plus 1 times RE plus UB. However, UB should stay here because it is known value. So this is the VC minus UBE. All right. Okay. And in this side of the equation, on this side of the equation, we've got the IB RB, IB beta plus 1 RE. Okay. So if we will extract the IB before the brackets and we divided both sides of the equation by the RB plus beta plus 1 times RE, we'll have the IB here. So it is equal RB plus beta plus 1 times RE. Okay. So how many it is? The question is, what is the beta? What is the IB current here? So if we substitute the every values, so it is 10 volts minus 0.6 volts over the RB, it is 220 kilos plus beta plus 1. Beta, it is 1. No, 2. No, 100. So this is the 100 plus 1. It is 101 times RE. Where is the RE? 510 I have one attack here, 510 ohms. Okay, so this is equal 9.4, yes, over, okay, using the calculator, so in fact it will be equal, I've calculated it before, so this is the 34.25 microamperes. That's the IB current. Okay, that's the IB current. So look, now we can coming back to the first equation. We've got the IB. We know how many it is. We have to find the UCE. We have to find the UCE. But we don't know what is the IC. However, if we know the IB, using this formula connected with the beta, we can find the IC. Okay. So IC, it is the beta times IB. Okay, so this is equal 100 times 34.25 microamperes. So as you see, this is around 3.33 milliamps. Okay. Okay. And great. So we've got the IC current. So from the first equation, let's finding the UCE. So the UCE will be equal how many? We have to just move the UCE to the right side of the equation, changing the sign, and we've got the result. So this is equal VCC minus IC RC minus IB beta plus 1 times RE. All right. So if you substitute at this moment the values, we'll get around, of course, it will be the 4.81 volts around. That will be the voltage drop on this transistor. All right. So these two values, IC and UCE, it tell you the point where your transistor is working. Okay, if you'll take the transistor and we wanted to show the relationship between the current, collector current, and the voltage drop between collector and emitter, the plot of that function for the bipolar transistor looks like that. It is something like that. And this is the function for some constant value of the IB current. For the different one, it will be looks like that. Okay, so as you see, any plots here, it is for the different IB current. And for example, look at what happened here. The voltage, the VCC voltage, it is equal 10 volts. So we've got 10 volts here. UCE, it is 4.81. It is around the half of it. Yeah. Okay. So the working point of the transistor here, it is very nice. Why? Because here this is the 10 volts. This is the 10 volts here. Why I draw it in here? Because if the base of the transistor will be 0, for example, or we'll put it here, so huge RB resistances, which gave us the very, very low of the base. It means that for such current equals almost to 0, or equal or almost to 0, the transistor is turned off. It means that the resistances between the collector and emitter is so huge. It means that even we've got the 1 kilos here, even we've got the, I don't know, 500 ohms around, and here we've got some mega ohms. So here on this branch, we'll have the huge resistances, which means the UCE will be equal almost 10. The whole voltage drop will be on the highest resistance here. Because according to the mega ohms, the 1 kilo, it is very, very low resistances. So as you see, that's why I draw it the 10 volts. In our case, we've got the UCE value for the DC analysis, of course. It is 4.81 volts. It is somewhere here. And let's say this point, it lay on the plot for IB, which is equal, like in our case, 34 around microamperes, which gave us the current, DC current of the collector equal 3.23 milliamps. So that's the working point of our transistor. Why it is so important? Why the UCE, it is around the half of the 10 volts? Because this moment, when we plug into the input our the waveform, for example, it could be the music from your, I don't know, MP3 recorder or something like that. We've got some music. Let's say this is the sine waveform, one tone, with some amplitude. What happened here? Look. What is the voltage? What is the potential of this base of the base point where we haven't the input signal? It is equal 0.6 plus voltage drop on the RE. Yes. So the voltage drop on the emitter resistances will be equal IE times RE. Yeah? Okay, so let's say this is around, I don't know, 2 volts, let's say. Okay, what happened when we observing the voltage signal on the input? All right, as you see, this is the AC current, this is the AC signal. So for the AC, we know that the capacitor, it is not the dielectric, this is not the insulator, for example. The AC signal can passing through by this capacitor. And what happened? This point, this 2, for example, volts, potential of these 2 points will be modulated with the input signal. So we're observing here the changing of the voltage drop, voltage potential in this point, like 2 volts, and we have the positive pulse of input signal, and we've got, for example, 2.5 volts. And again, we are going down. We've got 2 volts, and we've got here 1.5 volts. And again, yeah. So as you see, if we're observing the voltage fluctuation of this point, according to the Ohm law, we're observing the changing of the voltage drop on these resistances, Yeah? Because if this point is going up, yeah, the voltage drop on this resistor is decreasing. Yes. So the current is increasing. That's right. So as you see, the input signal, the voltage input signal is modulating the input base current. Yes. So if the signal is going up, the base current is going up too. So as you see, we have the modulation of the IB current like at the same time like the way like the input voltage. So the current is fluctuating here. If the current is fluctuating, it means that the IC current is changing too. However, this current is changed with the beta factor, like here, IB times beta. So this changes of the beta current is observing on the IC current multiplied by beta. Okay, so it is true. If it is true, it means that the changing of this current means that the voltage drop on the fixed value of the resistances RC is changed to according to this to the changes of the IB current. So if the voltage drop on this resistor is changing, and also the UCE is changing because we are because the resistances of the transistor between emitter and the collector is changing according to the beta changes, to the IB current changes, this point is starting fluctuating too. The potential of this point is going up or down, up, down, up, down. What does it mean? We've got the changing of this potential. So this is the capacitor. This is not the DC current at this moment. This is the AC signal. So this AC signal is passing through by this capacitor, and we're observing the changing of the voltage on the output. However, what happened here? The lowest changing of the current, beta current, produced the larger changes of the collector current. It means that the changing of the voltage potential or voltage drop here will be higher than in the base branch. So as you see, we've got the amplification of the signal. So that's why we can plug in here our loudspeaker or the headphones. Yeah. And in such way, we can build very quickly the simple amplifier. Great. Okay.
Can I ask a question?
Yes, Jakub.
We just calculated collector current completely ignoring RC resistor.
No, because this is here. You have to know that where it is the RC current. You have to remember IC current. This is the current which is entering on. It is entering to the collector. However, because here it is the one branch, one resistor, so it is not possible that this IC current is different than this one. Yeah? So everything is starting from this point. However, in calculation of the UCE, we are taking into account the RC, because
Yes.
current IC, it is times RC. This is the voltage drop on this resistances. So we are taking into account. I know that this calculation of the IC, it is just for the transistor.
I have here that we calculated base current, and then we can get collector current by multiplying base current by beta.
Yes, that's right. Of course, yes.
But what if? But if we would increase RC,
Yeah.
that current will be lower.
No, you will see what happened. If we will increase the RC, the IC will be the same. However, the UCE will be different. Will be the lowest one.
But at some point, we would UCE would be bigger than supply than voltage UCC.
It can be. UCE can be higher than the supply voltage. It is not possible.
What would happen? Clipping?
It will be going to the 0.20 or 0.2 volts. That's all. So that means that the IC current cannot go into the infinitive. Will be stopped. We'll have some saturation. And I'm just wanted to show you in this graph. Everything what we do using this calculation, we are making the DC analysis of this circuit. What happens with the AC analysis when we plug in the signal? We are changing the current of the beta. So it means that this point, in fact, will be going on this, will be going or changing on this plot. So, as I said, if the beta is modulated by the input signal, the IB is modulated by the input signal, it means that this point, this current also, and this point also. So we can say also the UCE is changing, is modulated. Yeah. So from the DC signal, for the DC point, where we not plug in the sine wave from here, this point is stable. However, if we'll plug in the sine waveform, we're observing the changing of this working point. It will be going here and coming back here and here, like that, giving us in the time domain fluctuation of the UCE point, like that. Here coming back. Something like that. Yeah, that will be our output signal. All right. So as you see, for this point, we are observing the IC current changes. Yeah. Yeah. But what happened? What happened when we supply so huge amplitude of the input signal? Maybe not some huge, but will produce too high changes on the output signals. It means that this point wanted to go farther than 10 volts. It can go farther than 10 volts because the 10 volts, it is the power supply of our circuit. So it is not possible to reach UCE higher than 10 volts. Yeah? UCE equal 10 volts It is then when the transistor is completely blocked, is turned off. It is huge resistances here, like the open circuit between the collector and emitter. So that's why the UC is 10 volts, not higher, because the UCC is 10 volts. So as you see, in that way, for the huge signal on the input, we'll have the situation like that. For the 10 volts, we'll have cut off the signal on the output. Because it's not possible to get on the UCE signal higher than 10 volts, higher than the VCC. Okay, what happened here? Look, here, this point, it is 0.2 volts. This is the saturation of the UCE. And as you see, this point will be going to down and going to 0. Do you see it? And coming back. So it is not possible to get the signal lower than 0, and in real lower than 0.2. So our signal will be going here and also cutting from this side. We have some unlinearity of the signal here. Why? Because as you see, here we've got this straight line of our plot, yeah? But here the curve of the plot are changed. So that's why this is an unlinearity function here. So that's why we have the unlinearity signal here near 0.2 volts. Yeah. Okay, so that you will see on the using the scope, you will see such signal will be looks like that if you will plug in too much input signal to your amplifier based on the one transistor. Okay, so that's why if you wanted to build the very simple bipolar transistor amplifier, you have to set your working point, DC working point, around the half of the maximum, half of the supply voltage value. Okay. So as you see, it was the example where we have any resistances. However, if you know how to find the DC working point for this amplifier, please imagine that you have to, for example, zaprojektować? Zapomniałem.
Design?
Yeah. Oh, sorry. Where you have to design your amplifier, you haven't got any values of resistances. So you have to know how to make it. That's why this condition that the UCE should be around the half of the VCC, it is very important condition for you, because you will, in the designing process, you will, first of all, you have to know what will be your VCC value. It depends on you. For example, you know that your very simple amplifier will be plugged into the, I don't know, the USB connector. So the maximum signal, it is 5 volts. Okay, so this is the first thing. You know that you've got the 5 volts of the input voltage, or of the supply voltage. All right, so at this moment, if you wanted to build the headphone amplifier, you know that the UCE should be around equal the half of the VCC. So it should be around 2.5 volts. And then you have to take the transistor for some beta value. In the data sheet of the transistor, you have to find the beta. You know what will be the UBE. It is around 0.65 volts for this for the silicon transistor. Yeah, so you've got it. Yes, and now you have to make this example, but from the end to the beginning. You have to find the IB. You have to determine the IC, for example. For example, let's say this is the 2.5 volts. So you have to divide the rest of the volts, 2.5 volts, on as a voltage drop on this resistor and this resistor. Yeah. So if you have it, so you have to fix it some IC current to find the RC, to get, for example, the 1.5 volts here, and here, for example, the 1 volts voltage drop. You have to find the IC. You have to fix it. You have to choose some current here. For example, I don't know, 5 milliamps. If you've got it 5 milliamps, then you'll be able to find the RC and RE. But if you will choose the 5 milliamps of the current, you have the beta. So now you can calculating what should be the IB to get the 5 milliamps of the current here. Okay, so such way you can find the IB. I've got IB. So now I have to build the equation for this branch. Yeah, because I have to take it into account the voltage drop on these resistances, which will be equal IB times beta plus 1 RE. This is the voltage drop here. And I have to find voltage drop on these resistances. Yeah? If you have it, I know the current IB, I can find the RB. Okay, so as you see, that's the way of, in the very short word, how we can design such circuit. Because in fact, in universities and at school, we get some examples. We have the input, the values, and we have to try to calculating something. However, in the designing, it's a little bit different. Yeah, this is the completely opposite way. Yeah? We have to know something about the conditions, and we have to find the values. In fact, okay, great. So the next thing, I think in the next example, you will be able to help me to solve it, and we will see how we're going. The next example will be like that. We've got the RB resistances equal 133 kilos, for example. RC, it is 1.8 kilos. EC, it is equal almost 10 volts. Okay. UBE, it is 0.6 because this is the bipolar transistor and made from the silicon-based material. And the beta is, okay, it's almost also 100, sorry. However, we have to find the DC working point of the transistor. So we have to find the IC and UCE. If it is the DC working point, this value we signed with extra Q letters. Okay, how it looks like the example. This is for example, EC, this is the supply voltage. This is the RC resistor. This is our transistor. And this is our RB resistances. Okay. So this is the voltage drop between emitter and the collector. And what do you think? What do we have to do firstly? Maybe you remember. We have to make it in the same way like previous example. What I done at the beginning? Do you remember? Solving the previous example. We have to
determine the direction of the currents and voltage drops.
Yes, that's right. That's right. So please tell me, what will be the current here? Maybe not. This is the current which will be going from the input power supply and should going to the ground, yeah? Okay, so we've got the point here, the junction. And at this junction, this current, it is split out by two currents. That's right? I think yes. And these two currents is entering to the transistor, and these two currents are leaving it by the emitter. Yes? Yes, okay. So let's name the currents. This current, it can be named like, please tell me, this one.
Base current.
Why? Because in fact, it is true that this current is going directly to the base. That's right? Through
yes.
this red. Okay. This is the IB current. Okay. What will be this current? What is
emitter current?
Sorry?
Emitter current, because this is the sum of base current and collector current.
Yes, excellent. Many students tell at this moment tell me that this current, it is IC current. It is not true, because IC current is here. Is here because the IC current, this is the current which is entering directly to the collector. Collector is here. Yeah, that's true. This current, it is in fact the emitter current. Yes. Why? Because the IC current plus IB current gave us the IE current. So the same it is here. All right. So very briefly, let's find the expressions for this very simple circuit. The first one, for example, let's take this loop. This one. So we've got the voltage drop on the RC, we've got the voltage drop on the RB, we've got the voltage drop between the base and emitter, and that's all. We have in the emitter resistance. So first example, first equation will be the EC. That's right. This is the voltage applied between the ground and the power point, minus voltage drop on the RC resistances, but in this case it is the IE times RC. Then it is the voltage drop on the RB, so minus IB RB, minus UBE. And everything is equal to 0. Okay, this is the first equation. The second one, this is for this branch. So this is the EC minus voltage drop on the RC resistances, i.e. RC, minus voltage drop on the collector and emitter. And this is equal to 0. That's all. All right. So we've got the two equations. 1, 2, 3. 3 unknown value. However, and again, we remember that IE, it is equal. Do you remember the expression for the IE? This is IB times beta plus 1, yeah? Like previously. All right. So as you see, we've got the two unknown value, two equations, in fact. Okay, so for the first equation, let's substitute the values or the expression for the IE. So this is the IB, minus IB beta plus 1 RC minus IB IB RB minus UBE. Yeah, this is the first one. And the second one, EC minus IB beta plus 1 times RC minus UCE. It is equal to 0. Okay, right. So from the first equation, as you see, we've got only the IB current. So we can find this current IB, and it will be equal the IB, the expressions with the IB, I can move to the right side of the equation, and it stay on the left side, it stay EC minus UB. And from this equation, I have to extract the IB and divide the above equation by the rest of the equation. So the expression. So it is the IB. It's going before the bracket. It is the B plus 1, beta plus 1, RC plus RB. Okay. Okay, I've got it. So if I will substitute the value, I will get the IB current equal 29 around, of course, 9 microamperes for that values. All right. So very briefly, I can find the IC Q value, yeah? So which is equal beta times IB. So this is equal to 29.9 microamperes times beta. Beta, it is 100. Yeah? So it is around 2.99 milliamps. One thing. So we've got the IC current here. And from the second equation, as you see, I've got the IB current, so I can find the UCE. So you see, I have to just move to the right side of the equation. I've got at the same moment expression for it. So if I will substitute then any values here, I will get the 4.57 volts. That's all. And this is our QCQ value, UCQ value. Yeah. So the DC working point for this transistor, this configuration, it is equal 4.25 volts as the UC, and current and the collector current, it is almost 3 milliamps. That's all. Yeah. So please remember, IC, it is here. This is the current which is entering to the collector. It is not here. Great. Today we've got the 4 hours, I think, yes?
I think not, but I can check this.
On the on Educacja, it says that we only have 2 hours.
Aha. Okay.
We had 4 week earlier.
Aha. Okay. So I missed something, because the last week I thought that we've got the 2 hours. Okay. So as you see, in the next the classes, I will finish the examples based on the transistors, and I wanted to show you how looks like the AC analysis of the transistor, of the amplifier based on the transistor. I think it is more interesting, and such examples show you how it looks like the real electronics. Yeah. All right. So I think. So please tell me, what you think about these examples? Do you understand it? So do you have some questions? Something is difficult for you? I don't know. Because I want to get some feedback from you. I don't know. I suppose that everything was presented very clear. I don't know. Maybe I'm wrong.
It looks simple, but I'm curious, how does it apply to the bigger picture? Hello?
Yes?
Can you hear me?
No, the quality is not so good. However, please go in, Camille.
The examples that you showed us are easy to understand. But
yes.
I'm curious, how does it apply to the bigger picture, like some circuit where this applies, where we can use transistors. But we'll see this later.
Mm-hmm. Yeah. I will show you. I try to show you, of course. Yeah, you have right. So everything at the first look looks like very simple. Yeah, but in fact, if you want to design something, yeah, that is so hard. Yeah, sometimes it's hard because you know the conditions. Yeah, many properties of your electronic circuits depends on you. You have to choose, for example, the correct, the bandwidth, the maximum, maximum current, which is taken from the power supply also. Yeah, everything, because in design process, everything depends on you. Yeah, so you have to decide it. What will be the maximum current? What will be the maximum voltage? What will be your the voltage supply also? Yeah, for example, the USB connector or not? Yes. So there's many cases, many things that you have to consider on the design process of, in fact, any electronic circuits. Yeah. So, however, we have to start with the very simple example with this with the basic circuit, yeah, because we have to know how to solve it. Yeah, if you know it, then the designing process is much more simple. Yeah, this is typical. Okay. So we have to start on some level. Yeah, we have to start with this components, with this circuits also. So I think at the beginning, this type of example, it is enough. Yeah, it is enough. So in the next week, I will show you the next type of how we can make the polarity of the base, in fact, because as you see, I show you today the two types of it. The first one, it is the polarization of the base by the RB resistor, which is plugging directly to the power supply. The second example showed, or has showed, the different type of polarization of the base when the RB resistor is connected here, not to the EC, but here. And in the next week, I will show you, well, maybe I draw it here, the different type of polarization of the base using the voltage divider. It is commonly used setup, in fact. And I will show you how we can use the known theorems, like the Thevenin's one, to make calculation much more easier and faster. Okay, in such case. And also in the next week, I will give you some information how we can make the AC analysis of such circuit or such amplifier based on the transistor. Because everything what was done to this moment, it was the DC analysis, but AC analysis, it tells us what will be the gain of the voltage between the output and input. Yes. What is the gain amplitude of this thing? What is the effective gain of amplitude? That's the difference. This is the KU and KU SK. Yeah. This isn't from the Polish. It is like in Polish it is wzmocnienie skuteczne. So effective gain. Okay, I will show where's the differences, what we have to take it into account, calculating such value for this amplifier. We have to take it into account also our signal conditions, which means what is the input. In fact, from the signal point of view, it is the output resistance, yeah, RG. So we have to take it into account also. All right. So I suppose that you have the next classes, yeah. So please tell me, did you have the lecture from the Adam Wąż last week?
Yes.
Yes. So what was presented by the Adam? What part of the electronics? It was the polyphase system, maybe.
Yes, multiple phases. And math about that.
Okay. Great. Okay. So there's nothing about the two-port circuit. No. Okay. Great. Okay. So I think we can finish at this moment. So we'll see in the next week on the classes, and we'll have the 4 hours. Yeah, that's right.
Yes. Can I ask a question?
Yes, Jakub.
So from what I saw, bipolar transistors are used, for example, in amplifiers. MOSFETs are used in high frequency switching, power switching. Is there a use case for JFETs?
Yeah, of course. Yes. JFETs, for example, are used commonly used in the amplifier too, also because they have very huge input impedance.
As do MOSFETs.
As MOSFET, according to the bipolar transistor, in fact, they use in the integrated amplifiers or the operational amplifiers. They have the better the input parameters. Also, sometimes the MOSFETs are used also in the amplifier circuits, but as the output transistor, yes, where we've got the huge currents, in fact, and in fact from this transistor we've got directly connected direct connection to the huge power loudspeakers, for example. Yeah. So as you see, it is not good to say that okay, the MOSFETs are used somewhere, something is used in somewhere else. In fact, the many type of transistor you can find in many applications. Everyone, we can say that we can tell that mostly something in use, or typically such transistor is used in some application. Yeah. Okay. However, believe me, you can find the very good the amplifiers or something like that using the bipolar transistor also. It depends on the parameters of the transistor, the properties of the transistor, where are used, in fact. However, you have right that the MOSFETs are commonly used in the switching circuits. Yeah. Why? Because they are connected, because they are controlled or driven by the voltage. There is no, we can say that there is no the input current there. Yes, because we've got the gate is isolated, isolated to the drain and the source. However, of course, even if we have the switching circuit where we use the MOSFETs, because the switching, it means this is the unstable state, so the currents are also passing through by the gate. Yeah, because this is also the AC analysis, in fact. However, please, you have to be very careful about talking about something like that something is used, I don't know, for amplifiers, different are used somewhere else. No. In fact, you can find everywhere. Yeah.
May I ask the question?
Grzegorz, yes. Grzegorz, thank you for your examples.
Of course. So the typical characteristic of JFET transistor is the high input impedance?
Yes. The JFET transistor has a very huge input impedance.
Yeah. So it's like many times different from other transistors.
As I remember, this impedance is going to the 10 to 9, 8 ohms, even 10. Yeah, it is so huge. Yeah,
I was wondering because there are many projects with JFETs of radio receivers as the front end designed with JFETs. So that was.
Yeah, that's right. Yeah. Due to the highest impedance.
My power was cut off, and now I'm from a mobile device. But I've heard your discussion with, I think, Jakub about the use of the JFET.
Yes.
There's popular JFET 310, I think, which is very popular RF JFET. So they are widely used.
Yeah, in the RF constructs.
Yeah, in RF, yes.
That's right, because they have low the capacitance also, the huge input impedance, the lower output impedance, and the lower the capacitance. If you have the lower capacitance, it means that the bandwidth of your transistor is larger. Yeah.
At the cutoff. Yeah.
Yeah, of course. Yeah, you have right, Grzegorz.
Can I have, let's say, can we next week do some examples with P-type?
P-type?
Yeah, P-type.
Okay, I can prepare something about the P-type transistor. It can be. In fact, this is the same. Only the polarity are changed. I can show you.
But I remember that I had problems with understanding low side and high side, but this was with MOSFETs.
Okay. If you want, I can prepare something about the examples based on the PNP transistor. There's no problem. Okay. So okay, I think if there's no any questions, so thank you again for watching today classes. I suppose I think that you note everything. Yeah. Did you note everything?
Yes.
Okay, great. All right. So thank you again, and see you in the next week. Okay, on the classes. Goodbye.
Bye.